guys! Alright, so here we are again. We're taking a look at the very end of the study guide, and some of my students in my IC, they've requested specific problems. So when you're here in IC, you get to request whatever questions you want. So it pays off to be here. Alright, but anyway, so they were looking at some of these problems towards the end. So I'm going to start right here. This is page 453, number 20. Alright, so let's take a look at that guy. Alright, so let's take a look at the information that they gave us. So we've got moles, for us that is N. And then they say something about STP. And then what size container? Size container, that kind of indicates to me volume. Alright, so let's break down what STP is. STP is standard temperature and pressure, right? So they actually gave you temperature, and then they actually gave you pressure right there. So this is what you got. Did anything change? In other words, do you have a second volume? Do you have a second pressure, temperature? No? Well then, this involves the ideal gas law. PV is equal to nRT. So they want to know what size the container needs to be, so they're asking you to solve for volume. Pressure is standard, so I'm going to go ahead and use ATM, atmospheres. I'm going to stick my V right there. N, they gave us 0.0459. Okay, so that's how many moles you've got. R, got to make sure you use the correct value, and since we have atmospheres, we're going to use 0.0821. I had a student ask me today at lunch, do we have to memorize the units, or the values of R? And I said, I think it's probably a good idea that you do. You should probably memorize those values. So if you've been slacking on memorizing this stuff, you may want to start doing that now. Anyway, standard temperature is 0 degrees Celsius, but I'm going to convert that to Kelvin. It's 273.15. And I'm using the 0.15 because it's exactly 0 degrees Celsius, like 0.000 with an infinite number of sig figs. Okay. Alright, so we're going to solve for that missing V over there on the left side. So grab your calculators. Alright, so when I multiply all of these numbers over here, I get 1.02933, and it keeps going. And hey, you got like one atmosphere over here, and then you got your V, and you're trying to get V by itself, so it's pretty easy. You see what I'm going to do? I'm just going to divide by 1, and that's itself, right? So that you get V. So this is volume. Question is, how many sig figs do you think we should use? So this one atmosphere, oh, wait. Alright, so the one atmosphere has an infinite number of sig figs. This guy right here has 3. Remember, zeros in the front don't count. This guy has 3 zeros in the front don't count. And this one's like, you know, got 5. So we have infinite, 3, or 5. What do you think we should have for our final answer? 3! Okay, so when we're looking at the value that we got, grab the first 3 numbers you got. 1, 2, 3. Do you need to round that 2 up? Sha. Got a 9 sitting right next to it. So volume is equal to 1.03, and the unit here is liters. Final answer. Alright, the next question we're going to look at is right here, number 25. I'm going to grab this one for you. Alright, here we go. So a flexible plastic container, flexible means that the volume can change. So like a, think balloon. A flexible plastic container contains this many grams. Now remember what I told you about anytime you see grams, I want you to think that you can get moles, which is N. Alright, when they give you mass, think moles. Okay, anyway, so they've got this mass of the helium gas and a volume. Okay, so there's your volume. If this many grams of helium is removed, oh, so that's another N value, is removed at constant pressure and temperature, so pressure and temperatures remain constant, what will be the new volume? There's our V again. So it looks like we got like this N and V thing going on, and you're like, what gas law should I be using for that? Well, if you remember your combined gas law, hold on, let me show you. N1, T2, or sorry, T1, that's 1. So equal to P2, V2, N2, T2. Okay, there's a combined gas law. Now notice you have 2 different N values, 2 different V values, so you can't use the ideal gas law. You're going to have to use the combined, but one of the things that they said in the problem is that pressure and temperature is held constant. So if pressure and temperature is held constant, you got to remove those. Like, they're remaining constant, they're not changing, so just like pop them out. So I got rid of my pressure. I'm also going to get rid of my temperature. What's left of that gas law? Like, we tore it up. All you guys have is volume and N. So here is the formula we're going to use. There you go. That's it. Okay, so now let's look at what were given. We were given this mass of helium, 0.860 grams. 0.860 grams of helium for our initial set, and then it says that 0.205 grams is removed. Huh. So this represents how much mass we started with, but we kind of need to see how it changed. What did it change into when we lost that mass? So we had 0.205 removed. 0.205 was removed. Okay, so if we remove 0.205 grams of helium, how much do we have? So I'm going to take 860, subtract 0.205. Looks like it changed to 0.655 grams of helium. Okay, but as I'm sure you already know, we can't use mass. We need moles. So what we're going to do to both of these guys is we're going to convert both of these guys into moles. Alright, so let's do that. So we start off with this many grams of helium. I'm going to convert to moles. So you got to find the molar mass of helium. Molar mass of helium is 4.0. So 4.0 grams represents 1 mole of helium. Alright, so let's figure out what those are. Here we go. 0.860 divided by 4. Alright, and this equals 0.215 moles. Do the same thing for the bottom. 0.655 divided by 4. And I only want 3 sig figs here, so let's do some, a little bit of reduction, 0.164 moles. So this is the initial amount of moles, and then we lose a little bit of helium, and this is our final number of moles. Alright, so let's go back over here. Let's see what else we got. Did they tell us what the initial volume was? Yeah, they said the initial volume was 19.2 liters. Alright, so initial volume, 19.2 liters. I'm sticking that on the top. Initial number of moles was 0.215. Alright, we lost a little bit of helium, and so the number of moles changed to 0.164. 0.164. And they want to know what the new volume is, so V2. Alright, let's hook it up. Do a little bit of math here. If you guys want, you can do some cross-multiplying. But let's see. Take a minute, pause the video if you want to check your results and just do it for yourself. That'd be good practice. For V2, I got 14.64558 on my calculator, and I'm going to reduce that to 3 sig figs. 1, 2, 3. Do you need to round the 16 up? Or I'm sorry, the 6 up? No. So V2 is 14.6 liters. And that should kind of make sense because it looks like you lost gas, and if you lose gas, you're not going to have the same volume. The volume is going to shrink down. The initial volume was 19.2, and we shrunk down because we lost some helium down to 14.6 liters. Alright, the next problem that we're going to look at is this guy right here. This is number 30 from page 455. Here we go. An ideal gas has a volume of 30 liters. If the number of moles of gas and temperature are doubled while the pressure remains constant, what is the new volume? Alright, this piece right here seems to throw students off when they hear me say ideal gas. They start thinking STP, 22.4 liters. But what you have to understand is, I remember us doing a video, it was Crash Course Chemistry. You guys remember that? And they discussed on the video how ideal gases, they just behave ideally. Because real gases, they actually are attracted to one another. And when you get a container of gas, and you shrink it down by decreasing the volume, eventually when you chill a gas, you could eventually get to a liquid, right? Like gases turn into liquids. And the way that process works is that the gas particles actually become attracted to one another at low temperatures so that they can become a liquid. So when you get down into those cooler temperatures, the gas particles will start to attract one another, and the volume that you think it is, it'll actually be less than that because they're starting to attract each other at cooler temperatures. So when it says ideal gas, it just means that it's behaving ideally. All right, looks like you got a volume of 30 liters. And it says if the number of moles in the gas, and the temperature are doubled while the pressure is remaining constant, what's the new volume? So they're looking for V2. Okay. Well, if you don't know where to go, my biggest suggestion would be look at the combined gas law. Anything that's being held constant, you can just remove. And that's always like a really good starting point. So let's just kind of check out that combined gas law one more time. So V1, P1, N1, T1 is equal to V2, P2, N2, T2. Now, did they say anything was remaining constant? Yeah, pressure is remaining constant, so I'm going to kick that out. Goodbye. Okay, did anything change? What did they say changes? Number of moles of gas and the temperature are changing. They're looking for that new volume. So it looks like the only thing we could eliminate was the pressure. Alright, well, let's see if we can organize some stuff. We got our initial volume, initial number of moles, initial temperature, and then we have our final volume, final number of moles, and final temperature. Can we fill any of this in? Well, yeah. This one's easy. This is 30 liters, right? Got that. But it says that everything else is doubled. Everything else is doubled. So you know what that means I can do? I can just put some fake numbers in here. If we initially had 1 mole, how many moles are we going to have over here? 2, because it's doubled. And if temperature over here is 1, what's this temperature going to be? 2. See how I just like kind of faked numbers there? And they want to know what that new volume is going to be. Alright, let's fill in some stuff. The initial volume was 30 liters. The initial number of moles is 1. Initial temperature is 1. Alright, we just made those numbers up. We don't know what that second volume is going to be. Okay, the number of moles doubled, and the temperature doubled. So if you want to, I can kind of simplify, but basically it looks like this. 30 is equal to V2 over 4. Guys, how do you get your second volume? It's 30 times 4. Alright, what's 30 times 4, guys? 120, and the unit here is liters. Final answer. Okay, next question we got right here is number 36 from page 459. There you go. Okay, so we got the volume here. We know that it's propane. Here is a pressure. So we got volume, we got pressure, and a temperature. Oh, there we go. There's our temperature. What is the mass? Now careful, when you think mass, I want you to remember that that could also be moles, okay? Alright. So it looks like we got volume, we got pressure, we got temperature, we got moles. Did any of those values seem to change? Do you have a second value for any of those? A second volume, a second pressure, temperature, anything change? No. That right there tells you PV equals nRT. Okay, we're using the ideal gas law. So let's fill in what we got. Well, we got a pressure here of 1.00 atm. We got a volume of 2.00 liters. They're looking for the mass, but I think we kind of need to solve for moles. So I'm going to put an N right here. We're going to solve for that. Make sure you use the correct value of R since we have atmospheres. Atmosphere liter over Kelvin mole. And then T. T is negative 15, so be really careful with the math over here. make sure on your calculator that you do negative 15.0 plus 273.15. So be careful over there when you get your temperature, okay? All right, I'm going to pause the video. Go ahead and pause the video for yourself and see if you can get the right answer. Let's check your math. I'm going to solve for the number of moles first. Okay, so you'll notice that I rounded my answer to 3 sig figs. Just remember, zeros in the front don't count. So the original value was 0.09436. So the 6 rounded the 3 to a 4, and that's how I got that answer. So that's how many moles we have. But that didn't really answer the question. They want to know the mass. All right, how many grams, in other words. We know how many moles there are. So in other words, guys, you're doing a conversion from moles to mass. So we've got the formula. The correct formula for propane is right here at C3H8. So let's get the molar mass of this guy real quick. I got a molar mass of 44.0 grams per mole. So coming down here, you see you've got your moles already. I'm going to go ahead and just convert this right over. I'm going to do a little bit of stoichiometry, okay? So you got moles here, cross cancel. We have 1 mole. 1 mole of propane is equivalent to 44.0 grams. So I'm going to put 44.0 grams on the top. All right, let's solve it up. And keep it to 3 sig figs, okay? I got an answer of 4.15. Again, 4.15 grams. So that would be your final answer right there. Okay, everyone, this last question right here is not extra credit. It's actually an extra problem that I added because I didn't think that the bookwork was very, sufficient, because you guys have some questions on your test that the book didn't cover in depth, but I did. So this last question is not extra credit. It's actually a mandatory problem that I want you to do. And it looks like this. All right, we have a 3.40 liter container. It has this many grams of oxygen, this many grams of chlorine, this many grams of carbon dioxide. What's the total pressure? Oh, sorry, the total pressure is 159 kPa. Excuse me, what is the partial pressure of each gas? All right, everyone, there are 2 different ways you can think of partial pressure, and we kind of reviewed this, but I'm going to do it again. The total pressure of the system could be the sum of all of the partial pressures, right? We got that. But there's another formula you have to remember for partial pressure, like the whole area. When you're thinking about partial pressure, there's another formula that should come to mind. And it looks like this. The partial pressure of any gas is equal to this mole fraction thing. Mole fraction times the total pressure of the system. All right, and there's 2 different ways. This mole fraction has to be less than 1, and there's 2 different ways that you can get that mole fraction. 2 different ways you can do it. You can do it by taking the number of moles of the gas that you're trying to find the partial pressure of. So I'll just say number of moles of gas you want the partial pressure for, divided by the total number of moles of the system inside the container. So I'll just say the total number of moles in the container. That's one way to get your mole fraction. The other way to get it is you take your percentage. Sometimes some problems give you percent, and you just change your percent into a decimal. And you guys know that all you have to do is just divide by 100, right? And that changes the percent into a decimal. Okay, so that was a good review. Which one do you think we need to use? The first formula or the second formula? The second formula involves moles. Now I understand that you've got mass up here, but we could easily change our mass into moles. So first formula is not the appropriate formula to be using for this question, okay? Anytime you see mass, anytime you see moles, you got to think about this second problem, okay? And they're looking for the partial pressure of each gas. They're not looking for the partial pressure of like one missing gas or something like that. If they were looking for the partial pressure of one missing gas, you would use that first formula, but that's not what we're looking for, okay? All right, so let's move it. Let's do this. All right, first thing I'm going to do is I'm going to change each of those masses that they gave us into moles. This is how many grams of oxygen we got. This is how many grams of chlorine I've got. Notice I know when to double up the formula. Do you see how I'm putting a subscript of 2 on those? you should also know when to do that, okay? So make sure you got that straight. It's basically any gas that is not a noble gas, you need to double. Alright, so I'm going to change all of these guys into moles. Go ahead and pause the video if you'd like. See if you can do this for yourself. Okay, so I rounded each of these moles to 3 sig figs. So we're looking for the partial pressure for each of these gases. And in order to do that, if you refresh your memory, you kind of need to have the total number of moles inside the system as a whole. So these 3 values that I have lined up, I am going to add them up. Now when you add them, technically the rule is you round to the least number of decimal places. And for this one we have 3 decimal places being the least number of decimal places. So when I get my answer here, I'm actually going to round to only 3 decimal places. Okay, so the total number of moles in the system is 0.255. Alright, let's start going through some partial pressures. So you need to solve for the partial pressure of O2, partial pressure of Cl2, and the partial pressure of CO2. And to do that, you need to multiply the mole fraction by the total pressure of the system. So for this guy, I'm going to put 0.109 on the top, 0.255 on the bottom. And the total pressure of the system should have been given in the original problem. Let me go back. Total pressure of the system was 159 kPa. Alright, keep it going. And one more. Alright, I'm going to go ahead and stop the video here. I hope this was helpful, and good luck on your test.